Yeah, so I'm just going to show a couple of tricks that I recently learned. You know, spent a couple of days learning how to do those 5 lines of code. Figure I'd share the wealth. Maybe we won't go the whole time. I have some other things to talk about that I'm not entirely sure how beneficial they are, and maybe others can do a little experimentation as well. But I'll demo those as well. So first off, is everyone, oh, Nariman is here. Is everyone more or less familiar with the like split, apply, combine strategy?
That's new to me, but I'm game.
Okay.
You don't worry about explaining it.
Oh, okay. Well, it's basically where you take a data frame and you sort of define groups of rows, and then you split those groups into different parts, and then you apply like a function to each group, and that each function produces a data frame as a result, and then you take all the resulting data frames and you stitch them back together into one data frame. So it's like a split, apply on the pieces, and then combine the results.
Got it.
Used pretty popularly in the R world. dplyr does it quite a bit. There's a police car on my street. And I recently learned how to do it in Apache Spark. So I'm going to show you guys how to do that. Space police. All right, so I have demos here for how to do this in both pandas or in both Python and R. This is all Spark. So well, it's not all Spark. I shouldn't quite say that. In my first example here, the input table does need to be a Spark data frame in order to do this trick. And what we're going to do is, I'm just using the concept set members table as an example of something to work on. Some of this stuff is actually not useful. This is old, so we don't really need that. So what we're going to do is inside of our function, we're going to define a function. And that function should take 2 parameters. The first one is a group key, which we'll talk a little bit more about later. And then the second one is a data frame. And in this case, it should be like a sub data frame that represents a single group that we're going to define later. And it's going to come in as a pandas data frame. So you can do, whatever it is that you want to do with a pandas data frame. Maybe you compute some summary statistics, maybe you run a model on it or whatever. Here, I'm just going to grab, how many rows are in the data frame. And then I'm going to build a pandas data frame and return it. So here I'm just sort of saying, I don't know pandas all that well, but I do know one way to build a pandas data frame is as a list of Python dictionaries, where the column names are the keys and the values are the entries. And then we're going to do pd.dataframe and just give it that.
Can I ask a question?
Yeah.
What is group? One of the arguments in the signature there is group key, but it doesn't seem to be used in this.
Yeah.
Okay, so you're probably going to explain that.
Yeah, deliberately, because I'll be able to show another trick next with that. So in order to make this work, what we're going to need is the schema of what the function returns. So this is a Spark thing, and to sort of in a basic sense, we're going to return a pandas data frame that has a integer column and a double column. So in this case, I'm going to say struct type, and you give it a Python list of struct fields, and a struct field is like, here's the column name and here's the type that it's going to be represented by. So that's more or less the basic thing. Spark does have some pretty cool like struct columns. So you can basically shove a dictionary into a cell of a Spark table. It's got array columns. So you can shove a list into a Spark column, but I think those use some other, I'd have to look them up, use the types. And then beyond that, all we really need to do is we're going to grab our table, which should be a Spark table, and we're going to say group by, And then we give the column names that we want to use to define our groups. So here I'm saying concept set name and version will define the groups. And just to go back, if you haven't, if you haven't seen the concept set table recently, Elliot mentioned that he's new to N3C. This is a table that defines OMOP concept sets, sets of codes that people have defined. And there's sort of a name. And then for each concept set name, there might be multiple versions. Like there's a version 1 of the concept set and a version 2 of the concept set. So I'm going to say, let's group by those 2 columns. So this function should get called on every set of rows that constitute a single name and version. And then I call on the result of that, apply in pandas, and I give it the function that I want to have called, which is this one up here. And then I also have to give it the schema, so it knows what sort of stuff is going to be coming out of that function, so that it can be concatenated together.
Can I ask a question? And this is just a generic question.
Mm-hmm.
So how do you decide which columns you want to use to do the group by? Like, is it usually like a unique, I just pick the unique identifier in the data set? Is this like a generic thing, or?
Usually you would do this if you have some complex thing that you want to compute over groups of rows. So let's say I have a data frame and it's got a bunch of concept IDs and a bunch of person IDs, and then maybe, I don't know, information about that person. You might want to say, okay, about the people, like,
okay, so it's
maybe concept ID, person who had that concept ID, and gender. You can envision being the 3 columns, right? And your question is, okay, for any given concept ID, is there a difference in gender proportions of people having that concept ID? So you would group by concept ID, and then you can say for each set of rows that contain a single concept ID, give me a t-test over the count of people who are male versus count of people who are female. Is it a t-test? May not be a t-test, but in any case.
okay.
So you could do, basically allows you to do complex things with groups of rows defined by your own groups. And you can certainly do this, right? If you have a data frame and you wanted to do that kind of thing, you could write a for loop over it, right? You could just loop over all your different concept IDs, pull out the rows for a single concept ID, do your test, go on to the next one, but that's much slower. Especially if the data is too big to fit in memory, in which case then you have a for loop and you're calling collect, right? So you're sort of saying Spark data frame, filter it, and then collect it so I can work on it. Then get me another Spark data frame, filtered, then collect it so I can work on it. And that's super duper slow. So this is much faster to do this kind of thing. And I would run this for you. It just takes a few seconds, but in any case, we see the result here. So for each, we have basically a stack of these data frames that are returned here. So we have a result count concepts and an answer to like the use of universe and everything column. Now you'll notice that we lost the grouping information, right? So these rows here might be from a particular group. Or this one, I forget exactly. Yeah, there's only 1 row per group. So this one is from a particular group, but I don't know which group it was, right? So that's what the group key is used for. In order to learn a little bit about that group key, I have another example here. So one of the tricks that I ran into when working with these kinds of things is debugging these internal functions, right? Like, I don't know pandas that well, and I had a bunch of errors. The problem is, if you were to do something like print from inside of here, the printed logs are not going to go to the logs that I see. The reason being is that what this line is doing is it's sending to the different machines in the cluster this function as well as the data that it needs to work on. And so this is called on a different machine, oops, than the one that is sort of producing the logs. So the trick that I found is you can raise a value error in this function, and that sort of gives you something on the output to look at. And it might be possible, I don't know, for example, if you do this in a code repo, if you can set a breakpoint inside of these or not, that might be something you can do.
I
But in
don't
any
think you
case-
can. I tried that.
You can.
I don't think you can, but
Yeah,
I wouldn't
yeah.
swear to it.
Yeah. So this is a handy way to sort of, just, hey, for one of these partitions, show me something, right? And so when you do this, if I do this for the group key down here in the logs, you see it right there. And so I can see that for this particular run of this function, group key is a tuple, which has the name of the concept set and the version, which are the things that we grouped by. So then if I want to get that grouping information back in my output, it's reasonably easy to do. Now that I know what group key is, I'm just going to say, all right, I'm going to add to my output a concept set name column, which contains the first entry of the group key, and a version column, which contains the second entry of the group key. And I also have to add those to my schema in the output so that it knows that it's going to be getting a string out and an integer out. And then there's the result. Any questions so far? Cool. One thing to know about this is that if you're grouping by a column, because what comes here is a pandas data frame, and you're going to return a pandas data frame, an individual group has to be small enough to fit in a single pandas data frame on a single execution node in the cluster. So if you were doing something like grouping by data partner ID, you might find that it doesn't work because one of the data partners has so much data that you aren't going to fit it into a single pandas data frame to run this function on. In which case you might need to group by multiple columns or something like that to make your group smaller.
And does that become obvious because you get an out of memory error or something that lets you know you've hit the limit?
I don't know. I think out of memory error would be the one because whatever we saw when we raised an error in our function, it sort of got thrown back. So there should be some sort of unable to allocate memory or something that gets tossed back to the logs.
Is it true though? Presumably you wouldn't know what exactly that error was unless you raised a value error inside of that function that you were calling, right?
Well,
Because
if you try and
go ahead.
Well, I guess it depends on what the error gets thrown. I mean, if I just say test equals 2 plus other, that'll create an error, right? Just in the attempt to execute this function, that'll get thrown back in the logs. And so presumably, though, again, I haven't tested this, if the group is too large, it'll throw an error back that'll also be captured in the logs. And hopefully the error says something about, out of memory.
So, sorry, I know this is a late question, but why do we need to define schemas again in Spark?
Well, that's a Spark question I don't know the answer to.
Is it like I'm just constructing some table structure on the fly just for the sake of doing this? Is it something like that? It's not really a table. I'm just trying to.
I think everybody will correct me if I'm wrong, but I think it's because this under the hood here is Java, which is strongly typed, so it needs to know exactly the types of everything that it's making the data for, because it doesn't like to do coercion.
Okay, yeah, that makes sense.
Yeah, that sounds reasonable to me.
And you have to add as many. So if you want to see a column in the output, it has to be added to the schema.
Correct.
So if I'm just checking to see if I follow what's going on here. On line 30, group by is a pyspark function, apply in pandas is a pyspark function, and answer is going to be a Spark data frame.
Correct.
Okay, good, thank you.
So one last thing here. So one thing you can do is, let's say I wanted to pass another parameter to the function, but because this function is going to be called for me, I can't really specify what the parameters should be here. So one thing you can do, and it's reasonably easy, is you just define sort of a global variable here. And let's say I have this special list. When the function gets called, it's able to access that global variable. So here I'm saying, okay, if group key at 0, which is the concept set name, is in the special list, then I'm going to define an isSpecial variable to be true instead of false. And then I'm going to return that in the output. So basically, I'm accessing this variable from this outer scope of the function, which is usually, not a good idea in programming practice. But in this case, it's very helpful because it allows me to sort of package up additional data and send it along so that it can be used inside this function when it lands on the backend executor. That does mean that this bit of data sort of gets sent along with the sub data frame and the grouping key to be run back here. So this probably shouldn't be too huge, right? If this was like an 18 billion row data frame, pandas data frame or something, then you're going to be sending a lot of data back along with it. But for the most part, you don't really run into those kinds of issues. So that's a handy way to sort of do something in your function that gets executed with additional data that you want to define outside.
And the reason why you did that is because you can't pass the apply in pandas function. You can't pass parameters that are not data frames.
Right. This is going to be called for me, and it's going to give me it only applies the group key and the sub df.
I see. So you couldn't on line 12, you could not add any other parameters.
I don't believe so.
Okay, got it. Thanks.
All right, so that's basically the thing for Spark data frames in Python. You can do the same thing in R, and it actually looks pretty similar. In R, we have more or less the same thing. We have a function which takes the group key and the sub df. Here, I'm just going to count, number of rows, and then I'm going to return a data frame, an R data frame, which has basically the same thing, 2 columns, result concepts and answer to life, the universe, and everything. And then in R, we similarly define the structure schema. The functions look a little different. There's a struct type function, and you give it struct field, which takes the column name, and then type of column, column name, type of column. And then in R, the function that does this is called gapply, and it takes the data frame, a vector of column names that you want to use for grouping, the function you want to call, and then the schema. And then you get the same thing that we saw in the Python example. And the error debugging trick works more or less the same, though there's a couple of things here. First off, let's talk about the debugging trick. In this case, I wanted to see what was in that group key parameter, but if I did a print, I wouldn't see it in the log. So I'm gonna use the stop function in R, and that throws an error, much like raise value error does in Python. However, what I wanted to do is to sort of get a printout. And when you have a stop function call, like if you were to stop, you can put some data here. So I could say, some data frame, and it'll call stop, and it'll log that data frame in the stop, but the formatting will be awful. What I really want to see is the format of the data frame as R would print it. And the trick for doing this is to call whatever it is that you want to sort of visualize, call the print function on it, and then R has this capture.output function that I'm going to call on that result. And instead of actually doing the print, it's going to sort of grab what would be printed as a vector of strings. Then I'm going to paste all those vector of strings together into, which are basically lines with line breaks in between them. And then I'm going to log that result. So this is basically saying, throw me the string that would be printed if I were to print this thing. And in the logs, we can see, here's the result right there. So in this case, the group key is an R list of 2 elements where the first element is the concept set name and the second element is the concept set version. One thing to know here, I'm using the pipe operator from the Magritte or Magritte R package. And in order to actually use that, you need to load a package that brings that in. In this particular case, you got to do it inside the function. The reason being, if I were to do this outside the function, when this function gets called on the backend machine, it won't have access to that library. But if you do it inside the function, then it does. And this is actually different from Python, where Python, if you do an import up here, it is accessible inside of that function when it gets called, but in R, it's not. So load up your libraries inside these functions if you want to use them. All right, and then we can see, oh yeah, we saw the error there. So then if I want to, again, add those grouping columns, I'm just going to say, all right, my result is going to be a data frame for each subdata frame. And then I'll add a new column name, which is the first entry of the group key list. And then I'm going to add a version, which is the group key entry, the second entry of the group key list. And of course, I have to add the additional struct fields in the output so it knows what I'm going to do. And in that result, we get, now we get our group information there as well. Yeah, useful. Oh, go ahead.
Continue, yeah, go ahead with the R's, because I was gonna go back to the pandas, but yeah, I'm not gonna interrupt you for the R.
I believe both Python and R have a version where what comes back is not a Spark data frame, but a native data frame. So there's a version of this called gapply collect, which basically does this and then collects the result into an R data frame and returns it. I think it doesn't take the schema, actually. It figures out the schema, which is interesting. But in this case, I would probably just recommend to say, if you need it as an R data frame, and just say our answer would be like collect answer. And that'll convert it from a Spark data frame into an R data frame if you need it that way. And then similarly in R, you can do more or less the same thing. If you have some extra information that you want to pass along, you can define it outside. Look, that's what happens when I mix my R and my Python. And then from inside, you can just access that variable. So here's that special list, and I'll check to see if the concept set name that I'm working with is in that special list. And if it is, then I'll define a result is special is true versus false on that thing. And of course, I've got my extra bits added to the schema. So now I have my is special. A couple of them should be true here. But in any case. Okay, Narman?
Yeah, so in the pandas part, I think in reality, what everybody wants to be able to do is like, if I'm familiar with pandas and not so much with the Spark statements, then I just want to be able to write things pandas way, like as far as the code goes. So I want to use pandas commands, but I want, when I finish, working on my transform, I just want to add those statements that you explain, like the function, the custom function, and then the apply to panda in pandas at the end. Is this a good practice or?
If you really want to just work in pandas, you have the option of saying, give me my input as a pandas data frame.
Okay.
I didn't know if did you know about that one already?
So when I do that, and let's say I'm combining two data frames, and one of them is too large, the other is smaller, that's when I start getting those out of memory errors and stuff like that. So my understanding was that, when I follow this technique that you explained, but I still want to use pandas on some of the data frames, I can still do that and I get a good performance. Is that, I'm not sure if my question
You
is.
can, if you have multiple inputs and one of them is really big, you could leave it as a Spark data frame. And if one of them's sort of small, you can leave it as a pandas data frame.
Okay, and for the Spark data frame part of it, I can use your approach where I can
Right.
do the subframe thing.
Yep. The other nice thing is if your secondary input is a pandas data frame, right? Like I had, secondary input is other PD input, where other PD input is up here. You can access other PD input up here.
That's exactly, because usually we
Right.
want to join, let's say Johanna's table, which is large, with some other small table like concepts, drug concepts or something like that.
In that case, so this is still probably primarily useful if you want to apply a function to different groups of rows in a really big data frame. Right, because that's what we're doing here. The fact that we can send in auxiliary inputs as a pandas data frame is handy, but really the main purpose here is to be able to apply a function to different groups of rows.
Yes.
If you do want to do like a join where you have a really big table and then a really small table for the join, you can do what's called a broadcast join, which tells Spark, hey, and you do this on two Spark data frames, which tells Spark, hey, take this small one and send it out to all the executors and then do the join, because there's no reason for this one to be shuffling data around when you don't really need to. You can just have a full copy of the one side of the join. And that is covered in the training portal. There's a optimizing Spark performance document that Saad had put together, and you could check that out too for looking at that one.
Yeah, I know Justin just shared the link for all tutorials. Yeah, thank you.
All right. So now I'll get into the stuff that I'm a little bit less familiar with, and I'm still kind of running tests on to see how it works and how well it works in our context. But so hopefully you guys are familiar with when you have a Spark data frame, it's broken into partitions, right? So it could be massive, but it's broken into chunks or partitions. And those partitions live on different backend machines in the cluster. And so, for example, when we go up here and we want to partition by or group by concept set name and version, a particular group of rows that's defined by those two columns might have some rows in one partition and some rows in another partition and some rows in another partition. And so when this function gets called, in order for it to produce a pandas data frame to give to this function, it has to grab those rows from the different partitions that match that group and pull them all together. And that happens like over a network connection. So it's slow to do that. It's actually a collect operation. It would be really handy if for a given concept set name and version, all of the rows were in the same partition, right? And there's a way to do this. Let's say I want to try this with the person table, where I have person ID. So for example, maybe I want to do an operation where for every person ID, I want to collect all the rows for that person ID, do something with those rows in my split apply combine business, and then put them all back together. And so we can use the repartition function to do this. The first thing to know is that if you have a Spark data frame, you can call repartition and give it the number of partitions you want to use. Here I'm using 200, which is way too big for this particular table, which only has 116,000 rows. There's sort of a sweet spot for the number of partitions that you should have. And usually if you're not calling repartition, right, it sort of figures out the number of partitions it should have. And then you just kind of work with the tables. And so you can actually sort of forget about partitions quite a bit when you're working, with Spark data frames for the most part, because it sort of automatically handles it. But you can explicitly tell it to use a particular number of partitions. And sometimes you need to do this. Usually it's because Spark has decided that a data set should be split into like 150 or 200 partitions, when in reality it's only one partition because it's just a really small data set and it doesn't need to be split over a whole bunch of different things. And that's also covered, this sort of like repartitioning to optimize the number of partitions is also covered in that training module that talks about optimizing Spark performance. But in this case, what we can do is we can also repartition according to a particular column. And what this does is it says, hey, create 200 partitions and make sure that everyone who has the same, all the rows that have the same person ID end up in the same partition, which is kind of handy. And you can envision that this would speed things up, right? If I were to do my group split apply combine, in order to do one of them for one of those person IDs, it doesn't have to collect in order to put all those rows into the same partition. They're already in the same partition. And you can also do it by multiple columns. So you could say group by person ID and, gender concept name or something. And that'll make sure that for a particular combination of these columns, they'll end up in the same partition.
Excuse me, Sean, just a quick clarification. You wouldn't actually, what you got on the screen right now, you wouldn't actually do that on the person table, right? Because the person table has one row per person, if I'm not mistaken. But you would do that on something like the condition occurrence or something, where you're going to have multiple conditions or multiple visits or multiple drugs or whatever it is. But you're doing it on a table where there's going to be multiple rows for each person ID.
Right.
Okay, just checking to make sure I follow what you're saying.
You're right. And in fact, this is actually, I'm doing some testing here to see if this strategy actually speeds things up. And so far the results have been a little bit mixed. I think probably because I'm using the SynPuff data, which is pretty small. And so I'm not going to see a huge bump in speed. But also you're right. I hadn't realized, or I hadn't thought of the fact that the person table only has one row per person. And so that's not a really good example of using the partitioning trick. But in this case, I ran some tests. And so I have I created a version of the data set that is in 200 partitions, just sort of, Spark, do whatever you want to do. I created a version that is partitioned by person ID. And then I created a version that is partitioned by condition concept ID. And then for each of these, I want to compute the exact same thing using that split apply combine strategy. So I'm saying, okay, group it by condition concept ID. So these are going to be the exact same, all three of them. And then I want to count the number of persons per concept ID. And so this is basically just grabbing from that particular group of rows representing a single concept ID, get the person ID column, run it through set to remove duplicates, and then give me the length of it. And then I'm creating an output data frame here where I have, how many people there were and what was the concept ID from the group key. And the result is sort of here. I did the same thing on the data set that's grouped by person ID. So this should actually be, oh, this one actually wouldn't be optimal, right? Because if I'm wanting to do a grouping operation on the conditions, ideally my data frame isn't partitioned by person, it's partitioned by concepts. So this should be sort of suboptimal. It's the exact same code, it's just working on a data set that's partitioned somewhat suboptimally. And then here, I have a version that is partitioned by the concept ID. And then I want to do the exact same thing to it. So this should be more optimal. I'm going to show you just a little bit of tricks for sort of looking at jobs. Some of this I still don't understand. But I'm going to open this in a data lineage. And this is the, whoa. I didn't need all that. And in fact, I'm not really going to use it. I could have just opened the data lineage app and you know, from over here and sort of started with an empty graph. And what I'm going to do is I'm going to add all of the tables that are defined by that workbook, which is a handy thing to do. So I'm going to say add resources, and then I'm going to go find that training area, users group, that one, this one, that one. So these are all the tables that are defined by that workbook. And I'm going to open them in the current view. And then I'm going to take the ones where I did the group tests. That's this, and this. And once you have something in this view, even if it's successful, you can see the build information for it. So you can see when I hover over it, no, not that one. If I go down here and I go to history, I can see the different builds that there were for this one. And this one took 1 minute and 48 seconds. This one where I grouped it by person, which, as I said, should have been suboptimal, was 35 seconds. And then the one where I grouped it by the thing that I was actually operating on, the concept ID was 22 seconds. I think I need to do this with much larger data sets in order to really get a sense of, you know, is this helping or not? I also ran a few tests where I tried to do some inner joins. So for example, if I want to join on person ID, ideally, I should be joining on a Spark data frame that's partitioned by person ID against another Spark data frame that's partitioned by person ID. And it should be suboptimal to, you know, have one of them that's partitioned by person ID, but have the other one partitioned by something else, or vice versa, you know, the person table partitioned by year of birth against the condition occurrence by person ID. And then, you know, really suboptimally, if I have a data set that's partitioned by concept ID and the other one that's partitioned by year of birth, but what I'm trying to do is join on person ID, that should be not so useful. So over here, person, 20 seconds, year of birth person, 15 seconds, year of birth concept, 20 seconds, person concept, 21 seconds. So I didn't really get any useful information out of those tests. But again, I think, Hannah, you're right. I should try in a table that, you know, makes better sense than the person table, and use a much larger one.
Yeah, I wouldn't, to be honest, yeah, SynPuff data is just not,
Yeah.
Let's just say it's useful for demonstration purposes, but not for this type of study, I would say.
Agreed. The other sort of handy thing you can do is if, you know, sometimes if you're into like looking at your jobs, you can watch them run and see how they go. It's sort of fun to do. But after the job completes, it's not as easy to find that build information in here. You can get it when you go to the data lineage and you go to the history and you click on the build, and then you can see the build report. that is the thing that you can also watch as it runs live. And so it sort of tells you, how long it took, yada, yada, yada. And you can click on the Spark details to see about how the Spark job was sort of allocated and running. And now we get into like, parts of Spark that I'm just not as familiar with. Spark sort of has stages, and then within stages, there are tasks, and each task involves possibly moving data around the network and so on and so forth. But one thing you can do is sort of look at one of these stages and look at the stage details. And you can see, now these are my functions being called on every partition. There's 200 of them. And I can sort of see how many rows are read and shuffle right across things. And so that can be kind of useful, and you can sort of inspect how long each individual one took and so on and so forth. However, in my tests, I wouldn't have expected, especially in the one where I was doing the group. So for example, when I did my group by person, but I want to call my function by person, do my group by condition, and I'm going to call my function by condition. So this should be the best one where everything is split up properly. If I look at the build report on that one, again, I also see sort of some shuffle right here. So I'm not entirely sure, or shuffle read. So I'm not entirely sure exactly what these shuffle read metrics are. I got to dig deeper into Spark to figure out those kinds of things to sort of diagnose, which data is moving around and how much of it. In any case, the main thing here is this stuff up in the pandas and the R examples. And I also have this node. This is where I was trying the repartitioning by columns, and I wanted to like really actually verify with myself that individual rows did end up in one partition if they were in the same group. And Spark has this map partitions, which is sort of like the apply function we had earlier, except instead of by grouping of rows, it does it by partition. So you can say, for each partition, do this. Normally you wouldn't do this, right? Because who cares about the Spark partitions? That's just how Spark decides to organize its data, but it gives me a chance to sort of say, okay, for any given partition, what's in that partition? So I can compare it and make sure that things that are in one partition are not also in another partition. And it all verified well. So, but if you ever wanted to see that weird code. So that's my spiel. I did that when I was running. I had some complicated code where I couldn't load it all into memory. And so I had groups of rows, and I needed to do something complicated with each group of rows. And so I was doing like filter to those group of rows in Spark, and then collect them, and then operate over the collected result, and then do that in a loop. And it was taking like 3 hours to run it. And when I converted it to this split apply combine with pandas, it came down to like 3 minutes. So definitely helpful to speed up your code, even if you're not doing any repartitioning or anything like that.
Did you say 3 minutes?
Mm-hmm.
Okay.
All right. Any final queries, comments, or questions?
So I'm just pondering what you just, so it sounds like what you've taught us today could have two, I mean, you could be solving one or both problems of either out of memory because you're trying to do something with a table that's just too big, or it's not out of memory, but it's too damn slow. So you're trying to speed it up and doing what you showed us. Even if you didn't have memory problems, you could still gain some time advantage using the method you showed us today. Is that, do I have that straight? Okay.
Yeah. And it just comes down to, when you have a Spark data frame or chunks of a Spark data frame and it's converted into pandas, that's probably going to trigger a collect where the rows for that collector spread across multiple machines, and they need to be put on one machine to be in a pandas data frame. And so that's going to like draw a bunch of data. And if you're doing that in a loop, you're like drawing and then doing some computation and then drawing and then do some computation. Whereas if you do this split, apply, combine in pandas, you're farming out those things to, however many executors you have in the back end. And so each one is sort of doing these collects, but it's happening in parallel. Unless it's
Okay,
also
thanks.
group partitioned by that column, in which case it should be less, but I haven't verified that very well yet.
Mhm.
All right. Well, I'm going to stop the recording here. I'll hang out for a few minutes if others have other questions around whatever, or just want to chit chat.